Start recording. Okay, this is your second lecture for MAT 212. Okay, so in this lecture, what we're going to do is we're going to cover matrices. We've looked at vectors in the first lecture that are an example of matrices, but now we're going to look at matrices in general. So what are matrices? Matrices are basically rectangular arrays of numbers, right? So you have so look at the matrix A in equation 1. This matrix has m rows and n columns. Now, the matrix itself is denoted by an uppercase letter, and the entries are denoted by lowercase letters. Now, lowercase a, ij, I in red and j in green, they denote the element in the ith row and jth column. So a11 is the element in the first row and first column of A. A22 is the second element in the second row and second column. A12 is the element in the first row and second column, and so on and so forth. So A is an m by n matrix. So therefore A has mn elements or entries. All right, so let's look at how to add and subtract matrices. So if you want to add or subtract two matrices, you need to make sure first that both matrices have the same number, have the same dimensions. So if you want to perform the addition A plus B, A since A has m rows and n columns, B must also have m rows and n columns. B defined in equation 2. So since B must have, in our example, B does have m rows and n columns. So we can perform the addition A plus B. Let's call the result C. So the element in the ith row and jth column of C is Cij, which is actually equal to Aij plus Bij. Now notice something about these matrices, that the addition is commutative, meaning A plus B is the same as B plus A. And also because the addition of real numbers is associative, addition of matrices is also associative. So A plus the addition of B plus C equals the addition of A plus B plus C. Subtraction is defined similarly. So A minus, so if D equals A minus B, where D is an m by n matrix, of course D has to be an m by n matrix. So Dij equals Aij minus Bij, as in this equation. What about scalar multiplication? If we multiply each element, we can multiply each element of the matrix by a certain constant. That's scalar multiplication. Okay, so now we've learned how to multiply it by a scalar constant, matrices by a scalar constant. Now let's look at multiplication of one matrix by another matrix. Now, when we're multiplying matrices, of course, order matters. So when we perform the multiplication xy, we're left multiplying y by x. Or you could say that we are right multiplying x by y. Now, in order to perform the multiplication xy, the number of columns in x must be equal to the number of rows in y. Well, that's because we will be, in order to get the elements of xy, we will be taking the inner product of the rows in x and the columns in y. Now, for that to happen, the number of columns in x has to be equal to the number of rows of y. Otherwise, the inner product is not going to be defined. Now, let x be the matrix defined in 5. as in let X be an M by N matrix. Notice that I've gotten rid of the color scheme. And let Y be the N by P matrix defined in equation 6. If this is the case, then we can perform the multiplication XY because X has N columns and Y has N rows. So the number of columns in X equals the number of rows in Y, therefore we can perform the multiplication XY. And the result, as we shall see, is going to be an M by P matrix. So let's call the result Z. So to get the ijth element of Z, we perform the multiplication xik times ykj, then sum over k. K goes from 1 to n, where n is the number of columns of the first matrix, or the number of rows in the second matrix. Of course, the result is an m by p matrix, and therefore I goes from 1 to m, and j goes from 1 to p. Okay, so now let x be defined as our. Let's do a numerical example to make things clearer. Let x equal be the matrix in equation 8 and y be the matrix in equation 9. Let's form the product xy. Call it z. We know that x is a 2 by 3 matrix, sorry, a 3 by 2 matrix, and y is a 2 by 3 matrix. So you can perform the multiplication xy, and you know that the resultant matrix is going to be a 3 by 3 matrix. Let's call it z as in equation 10. So z11 is the product of the vector formed by taking the first row of x and doing an inner product with the first column of y, as in the green row and the green column. And so z1 equals 1 times 7 plus 2 times 10. Z12 is the inner product of the first row of x and the second column of y. Similarly, Z13 is the row and column highlighted in pink is the product of the first row of x and the third row of column of y. So Z21 is the product of the second row of x and the first column of y, as in the ones highlighted in yellow. Z22 is the product of the second row of x and the second column of y. And you can find the other elements in a similar fashion, and you should be able to finish this calculation. The answer is, of course, given by equation 16. That is the full answer. Similarly, yx is also possible. Why is that? That's because notice that y is a 2 by 3 matrix and x is a 3 by 2 matrix. So you can do yx, and yx is going to be a 2 by 2 matrix. Notice that yx is not the same as xy. Matrix multiplication is generally not commutative. In fact, just because xy exists doesn't necessarily mean that yx exists. Yx may not even exist. It may exist, but it may have a different dimension. Therefore, matrix multiplication does not commute. Now, however, matrix multiplication is associative, as in the product of. So if you have an m by n matrix A, an n by p matrix B, and a p by q matrix C, the product of AB right multiplied by C is the same as A right multiplied by BC, as in this expression on the right. In other words, of course, it doesn't really matter what order, what you multiply first, which two matrices you multiply first. Now, how do you prove this? Say you have a matrix D, and you call, let's say, D equals AB times C. Now let D be the Dij, with the entry in the ith row and jth column in D. Then, of course, D is an M by Q matrix because A AB is an M by P matrix, and C is a P by Q matrix. So D has to be an M by Q matrix. And of course, I can then go from 1 to M, and J can only go from 1 to Q. Uh, okay, so and we also let x equal ab and y equal bc. So then dij is of course equal to xil times clj, where L is summed from 1 to p. When this is equal to, now xil is of course equal to aik times bkl, because remember x equals ab, so you do the summation again, where k goes from 1 to n, times clj. And of course, because real number multiplication is associated, we can associate b and c, right? But this last product, right, summed up over L is basically y, yl, ykj. So this is equal to aik times ykj. But this is again, with this last summation here is this last summation here is basically your is basically a times y, the matrix a times y, but y is just bc. So this is, so what have we done? We've proven that AB times C equals A times BC. And so we have proven the associativity of matrix multiplication. Now, of course, you've already seen matrices before. Vectors are examples of matrices. Uh, 2 by 1 or 3 by 1. Two-dimensional vectors are 2 by 1 matrices, and three-dimensional vectors are 3 by 1 matrices. Okay, transposition. So when you transpose a matrix, right, you change, you interchange the rows and columns of the matrix. So aij, so if you have a matrix A, right, so aij is the element in the ith row and jth column of A. Now in this case, now if you take A transpose, that aij becomes the ith element in the jth row and ith column of A transpose. So for example, if you take the matrix X that we have already defined in equation 8. Remember this matrix? This one. We've already defined this. Now, it, this is a X is a 3 by 2 matrix. Now, when we transpose X, we get a 2 by 3 matrix, right? Now, notice that X12, the first row and second column of X, is 1. Sorry, the first row and second column of X is 2, right? X12 is 2. So X21, so when you transpose X, the element in the second row and first column has to be equal to 2. Now, if you continue this, you can go on and on, you get this for X transpose. Okay, cool. So now that we know what transposition is, we see that product, the transpose of a product is the reverse of the product of the transposes. All right, so AB transpose, right, provided of course you can multiply A and B, equals B transpose times A transpose. Okay, so provided of course you can multiply these matrices. Now, why is that the case? Now let's see v equal to AB. So of course, C can be written as, so Cij can be written this way. Okay, Aik times Bkj, then sum over K. Now, but then C transpose is AB transpose, and the Ij entry in C transpose can be written as C transpose Ij equal, of course, is equal to Cji. That can be written as Ajk times Bki. Uh, but then this is equal to this is, you switch to flip the indices, you flip jk to form kj, but that makes a transpose, akj transpose. You flip ki to give you ik, so that gives you vik transpose. But then because these are numbers, you can place the b in front, so that you get vik transpose times akj transpose. Now in this last summation, this last summation you can write as the ij element of v transpose a transpose, right? So therefore you have ab transpose equals b transpose a transpose. Okay, so you've got that covered. The assignment actually asks you to, no, yeah, the assignment actually asks you to prove something very similar with regards to inverses. Okay, now in the previous lesson, of course, you've learned about the dot product or the inner product, right? V dot W, this is equal to V1 W1 plus V2 W2 plus V3 W3. And remember, I said that the dot product is a 3 by 1 matrix, so you can write the dot product as a I'm sorry, as I said, that the vector is a 3 by 1 matrix or a 2 by 1 matrix, depending on whether you're dealing with three-dimensional and two-dimensional vectors. So dot product between V and W can be written as V transpose times W. And with the you can write the dot product this way, and with the rules of matrix multiplication, you get this. You should work it out and see why this works. Okay, of course, we may write the dot product as WTV. That's also possible. Uh, so and therefore you have now, because we can write the dot product this way. I'm remembering that the modulus of W, or the size of a vector W, is W dot W square root of, right? We can write the modulus of W as the square root of WTW, as in the highlighted equation. All right, square matrices. Now, square matrices are, of course, matrices for which the number of rows equals the number of columns. In general, a square matrix is of this form, given the equation 20. This is an n by n square matrix. It's called an n square matrix. Of course, the red elements are the diagonal elements, and the other ones are the off diagonal ones, right? So, uh, now, of course, the most important square matrix you will see is the identity matrix. The identity matrix is the matrix is denoted by I. Now you have a now along. Okay, so the for the identity matrix, all the elements along the main diagonal are equal to 1, and all the off diagonal elements are equal to 0. So the special identity matrix lies in the fact that any matrix, if you multiply it by the identity matrix, AI equals A. Also, even if you do right multiplication, IB equals B. Okay, so what you can do, you can test this claim for the matrix Z that we defined in equation 10, right? Check to see if Zi equals Z and Iz equals Z for the 3 by 3 identity matrix. All right, cool. So the inverse matrix, right? So let's say you have a square matrix A and you have a matrix X such that A times X equals I. Or you have a matrix Y such that Y times A equals I. What you do is you call X the or Y the inverse of A. Now, if now it may be that A does not have an inverse, right? So in that case, you say that A is a singular matrix. Now, if A does have an inverse, then we call a a non-singular matrix or an invertible matrix. Now, of course, if X, if the matrix A has a left inverse and a right inverse, as in if A times X equals I and Y times A equals I, then X equals Y. How can we prove this? We're going to prove this right now. So if you let X be the right inverse and Y be the left inverse of A, as in AX equals I and YA also equals I, so you must have X, which is equal to IX. Now I is YA times X. Now by the associativity of matrix multiplication, we may write this as Y times AX. But AX is again equal to I, as in because that is what we hypothesized. But then YI equals Y. So from here we have X equals Y. So the left inverse equals the right inverse. So they're not different, they're the same. So x equals y equals a inverse as required. Now, of course, when dealing with rotations, there's a certain class of matrices that will meet. They're called orthogonal matrices, and they have the particular property that the inverse of the orthogonal matrix is the same as the transpose of the matrix. Now we will look at orthogonal matrices again and again when when we're studying rotations, reflections, and so on and so forth. There's one in your assignment, and you're required to show that orthogonal transformation by an orthogonal matrix preserves the dot product, preserves the inner product. All right, so that's it for this lecture, and if you have any question, please please ask.